Okay, so a dilation is a change in size. So the shape of a figure is going to stay the same after a dilation. So if you start with a triangle, you'll still end up with a triangle. That's going to look similar. They're going to be similar triangles actually, like in this diagram I have down here. Right? They're not going to change. It's not going to change the shape, just the size. Okay. So there's two different brands of dilations. We've got an enlargement and a reduction. So an enlargement, it's growing from the original pre-image to the final image, and a reduction, it's shrinking. You can think of it that way, right? So an enlargement is going to have a scale factor that is more than 1. Okay, so if you have a scale factor of 2, for example, that means that a figure is going to double in size. If you have a scale factor of 3, then it's going to triple in size. A reduction is when the figure is getting smaller, and the scale factor is going to be between 0 and 1. Okay. So if you have a scale factor of 1/2, your final image is going to be half the size of the original, and so forth. Okay. So on this example, is the dilation pictured an enlargement or a reduction? Okay. A lot of people are going to look at this diagram and say, "Oh, it's an enlargement," because hey, it started small, now it's big. Well, that's because those people are thinking of this as a story going left to right, which is totally natural because that's the way we read in English, right? But you have to be really careful with the markings in the diagram because my story doesn't actually start with this triangle; it starts with this one. So I don't have the little apostrophes by the bigger triangle. So this is triangle ABC. This is triangle A prime, B prime, C prime. So this is after the transformation, right? So my original image is here. So I got to think in this particular story, it goes that way. That's my story, right? This is the beginning of my story. So this is actually getting smaller. So that means I'm going to have a reduction, okay? And then the scale factor, all I have to do is find some matching pieces, okay? So I've got the 6 and the 3, okay? So we're going to write the scale factor usually as a fraction. So the 6 and the 3 match up. You could also use the 4 and the 8. It doesn't really matter. And I can see in both cases the 6 is twice as big as the 3, the 8 is twice as big as the 4. Okay, so I'm going to make a fraction out of this. Some people are going to say, oh, I'll just do this. But that's actually incorrect because that would mean I'd have an enlargement, right? Because I'd have a scale factor of more than 1. So just make sure that you have your fraction flipped the right way so that it represents either an enlargement or a reduction. In this case, I already knew it's a reduction. And then you do want to reduce your fraction. So the scale factor there is 1/2, not 2, okay? All right, let's look at this next example. It's the same kind of deal, just a new diagram. And this diagram isn't to scale, but let's just go with the given info, okay? So an enlargement or a reduction, so I got to make sure I know where the story starts. This time it actually starts with the smaller triangle because I can see that's the original one because there's no prime letters there. My primes are all over here, so this is after the transformation. So this one I can see is an enlargement, and then the scale factor, I can choose the 3 and the 9 or the 4 and the 12. Okay, and so actually both of those are going to, whether I use 3/9 or 4/12, they would both reduce to 1/3. But wait a second, I messed up again, right? Because I had an enlargement, so I shouldn't have a scale factor. 1/3 would be if my triangle was shrinking. So this is incorrect. I need to flip this upside down. Okay, so I want to write 9/3 or 12/4 would work as well. Okay, and then I can reduce that, and you could write 3/1 if you wanted to, but that's fine like that. Okay, sometimes just so you know, doesn't really matter, but sometimes you'll see these scale factors written like this with a colon, so that means the same thing, 1 to 2, or you might see this as 3 to 1. but I'm usually going to write it as a reduced fraction. And you can write it as an integer if it has a 1 in the denominator. Okay? All right, let's move on to the next page. Let's actually do some dilations then on a coordinate grid. Okay, so this says dilate triangle ABC about the origin by a scale factor of 2. Okay, so usually we're going to be dilating about the origin, not always. So there's what's called the center of dilation. Okay, so this has a scale factor of 2, and it didn't ask me here, but just that that right there tells me that this is going to be an enlargement, and that's kind of helpful to have in your mind when you begin the problem. I know that this triangle is going to get bigger. Okay. Now getting back to this center of dilation, that means these points are all going to move away from the center of dilation. So these are all going to spread out, kind of like the Big Bang. This is the center of the universe. Got the Big Bang and everything's spreading out, right? And when those points spread out, the triangle is going to get larger. Okay. All right, so let's try this out. The easiest way to do this, I think, is just to figure out what the coordinates are at the beginning, okay? So what I can do, since the scale factor is 2, that means I can just multiply all of the coordinates by 2. Okay, so I know A prime then. Well, I can just multiply, hey, 1 times 2 is 2, 1 times 2 is 2. I just doubled A to get A prime. And I'll do the same thing to get B prime. Instead of 3, 0, I'm going to get 6, 0. 0 times 2 is 0, right? And instead of 4, 3, for C prime, I'm going to have 8, 6. Okay? And then I'm just going to plot those 3 points, and I should wind up with a triangle that looks twice as big as this one, but maintains the same shape. So let's see, 2, 2, be about here. And 6, 0, 2, 3, 4, 5, 6 zeros right here, and 8, 6 right about here. Okay, just gonna use this as a little straight edge because I left all of my rulers in my classroom, and I'm at home. Okay, and then I get a triangle that, yeah, that looks pretty decent, right? All the sides look twice as big as the original sides. The triangle's twice as large, okay? All right, so let's try the next one. Same kind of deal, except on the next problem, our scale factor is going to be 1/2, okay? So first thing I'm thinking about that, and you don't necessarily have to write it down, but I know that this is going to be a reduction. My scale factor is less than 1. And that means my triangle on this next problem is going to shrink. Okay? All right, so I like to just get the coordinates right away. So I'm multiplying everything by 1/2, which is the same as dividing by 2, right? So if I take -4 divided by 2, get that, -2 divided by 2, okay? And that's A prime actually, and then I'll do the same thing for B prime, dividing by 2 here. And C prime dividing by 2 again. So let's see, -2, -1. B prime is -1, 2. C prime is 2, 0. Okay, and often you'd want to label what the coordinates of these points are. I'm not doing that here because I've already done it up at the top. But if you didn't do it at the top, you could put it in your diagram as well. Okay, so there we go. And the center of dilation here again was the origin. So when it's a reduction, it's kind of like, you know, that's the drain in the sink, and you pull the stop and the drain, and everything kind of gets sucked in towards that, and you end up with a shrinking triangle. Okay, all right. So one thing we haven't talked about is a negative scale factor. You actually can have that, because I talked about, you know, a scale factor of more than 1 or between 0 and 1. Well, on this next problem, I've got a scale factor of -2, okay? And the easiest way for me to describe this is just to do the multiplication, okay? So just like on the previous 2 problems, I'm going to multiply by the scale factor of -2, so that means I'm multiplying all the coordinates by -2. So that gives me 4, 0 there. And -4, -6. And -2, +4. Okay? And let's just plot this and see what actually happens. So 4, 0, 1, 2, 3, 4. Here's A prime. B prime is -4, -6. Probably off screen here. Just give me 1 second. Here it is. And then C prime is at -2, +4. 2, 2, 3, 4. Okay. I'm just going to connect the dots to get my new triangle. Okay, so let's think about what has actually happened here. Well, I can see clearly that my new triangle is larger than the original. So I do have an enlargement. Okay, but then this is kind of interesting. If you look at the original point B and my final point B, my B prime, well, my original B was in the top right of this triangle, and B prime's in the bottom left. So what's actually happened here is this has rotated 180 degrees, okay? It's on the polar opposite, if you think about the origin. It's on the other side, okay? And the same thing happened with A. You can see those are on different sides of my center of rotation. So the whole triangle has, the original triangle has rotated around 180 degrees, and it's an enlargement, so it's doubled in size. So it's also going to be a rotation of 180 degrees about whatever the center of dilation is, typically the origin. But not always, as we will see on the next couple of problems. It's not always going to be the origin. Okay. All right, so let's move on to the next page. Okay, similar kind of problem, except what the? We're not rotating about the, we're dilating about the origin anymore. We're dilating about the point 1, 1. Okay? So these are a little trickier. What I like to do on these problems is to make myself what I call some crosshairs. So this is going to be, it's going to be like a new XY axis. Okay, so I'm just going to, you can do this with a pencil or whatever, but I'm going to mark the point 1, 1. Okay, this is my center of dilation, and then I'm going to put some dashed lines in here. Okay. So now this is a little tricky. I can't, even though I've got a scale factor of 2, so I know this is an enlargement. So my triangle is going to get bigger. If I was dilating about the origin, I could just multiply everything by 2. But I don't want to do that here. What I want to do is double the distance that these points are from the center of dilation. Double distance from center of dilation. Okay, so let's take point C. That's the easiest one to work with here. Okay, if I was dilating about the origin, it'd end up down here somewhere. Instead of at 1, -1, it'd end up at 2, -2. But I'm looking at the distance from the center of dilation, which is right up here. So I can see that's 2 units directly south of the center of dilation. So I'm going to double that distance. Instead of going 2 units south, I'm going to go 4 units south, and that's where C prime is going to end up. Okay? So let's try the same kind of thing with point A. And this is where it gets a little trickier. It's much easier when it's just on one of the crosshairs. But what I'm thinking on this next point is that, okay, going from here to here, I'm going to go left 3 units, okay, and then down 1 unit. And I want to double both of those distances, okay? So instead of going left 3, down 1, I'm going to go left 6, down 2, okay? So 1, 2, 3, 4, 5, 6, 1, 2. I'm going left 6, down 2 from the center of dilation, not from the origin, from here, right? And that's where A prime is going to reside. And that's the, well, I'll get to the coordinates later, okay? I'm going to do the same kind of thing now with point B. So I'm thinking, okay, if I go up 2 to the left 2, up 2 to the left 2, right? So I want to double that. Instead of going up 2 to the left 2, I want to go up 4 to the left 4 from the center of dilation. So let's see, 1, 2, 3, 4, 1, 2, 3, 4, and here's where B prime is, okay? I'm going to connect the dots on these and see how this looks. Okay, and on all of these dilations, you should end up with a triangle. It doesn't have to be a triangle, but you should end up with a figure that looks similar to the original figure. So if it looks warped, something went wrong, okay? So I can see, hey, it does look, actually, you know, if that's the center of the universe, I got my Big Bang, and things are stretching out, and it looks like the red triangle is twice as big as the original one, okay? Also, another thing you want to be careful of, when I give the coordinates, sometimes it's tempting to say that, like for C prime, that this is the point 0, -4, because it's 4 units below the center of dilation. But that's not the actual coordinate. So when you count the coordinates, make sure you use the original origin. So this is the point 1, -3. It's not 0, -4. 0, -4 would be down here, right? This is 1, -3. And then looking at A prime, I'm going 1, 2, 3, 4, 5, down 1. So 5 left, down 1. And then for B prime, let's see, 1, 2, 3, 3 to the left, 3 to the left, 5 up. Hopefully I counted right there, okay? So that's how you can dilate about a point other than the origin, okay? So you can go ahead and try the next one if you want, same kind of problem. You can pause it. I'm just going to get straight to it. Again, we're going to be dilating. This is going to be an enlargement, but this time we're going about -1, -1, okay? So I'm going to start by plotting that point. And then making some crosshairs so that I get a visualization of what I'm going away from when I've got my enlargement here. Okay, so the easiest point to deal here with is A, because I can see that's 2 units directly above that, so I'll just make it 4. Double that distance because it's a scale factor of 2. There's A prime, okay? And then let me try C prime, so I can see this is 1 right, 1 down. So I'm going to go from the center, I'm going to go 2 right, 2 down. I didn't quite leave myself enough space on there. There we go. Okay, but C prime is going to end up something like that. Okay, and then B prime, let's see. I'm going 1, 2, 3, 1, 2, 3, 4. So I went 3 right, 4 up. I want to double that. So I'm going to go 6 right, 8 up. 1, 2, 3, 4, 5, 6. 1, 3, 4, 5, 6, 7, 8. Just enough room. Let's B prime. Coaster out to connect the dots. Okay, and then I'm going to label the coordinates of those prime points. So let's see, this is 1 left, 1, 2, 3 up. This is 1 to the right, 1, 2, 3 down. And I've got 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6, 7. So this should be the 0.57 if I counted correctly. And there we go. That's dilated. I can visually see it's stretching out all those points away from the center of dilation. Okay, that's it for this section.